Okay, so now we've got four more types of radiation I want to talk about. They are electron capture, fission, and fusion. So first one here, electron capture. What happens here is that an inner shell electron that's surrounding the nucleus gets captured by the nucleus. So the nucleus absorbs one of the electrons that's surrounding it. And what would happen, do you think, when the nucleus absorbs an electron? Do you think that electron is going to react with the proton or the neutron? Robin says neutron, Joyce says proton. What's your reasoning? Why proton, Joyce? Why the neutron, Robin? Joyce is right. It's because of the charge. The electron, which is positively charged, is going to be attracted, or sorry, the electron, which is negatively charged, is going to be attracted to the proton because it's positively charged. Neutron is neutral, so it just doesn't care really either way. It's not attractive at all. But the opposite charges will attract, and when they do, we can predict what's going to be formed based on what happens to the mass. 0 plus 1 gives us a mass of 1. Negative 1 plus a positive 1 gives us a charge of 0. And what particle has a mass of 1 and a charge of 0? The neutron. You have to put a little n, a lowercase n, because a capital N would make it nitrogen, right? Yes, perfect. So electron capture then is kind of the opposite of beta emission. So instead of emitting an electron, I'm going to absorb an electron, and it just converts here then protons to neutrons. So for example, mercury 197 decays by electron capture. And it forms gold 197. So notice on the left-hand side, total mass is 197. Total mass is 197. On the left-hand side, my total positive charges are 79. And on the right-hand side, total positive charges are 79. Everything is still conserved like it always is. But because I captured the electron rather than emitting it, I'm no longer emitting it, I'm picking it up. This is now one of my reactants. It's on the left-hand side of the arrow. Everybody see what's going on there? Could you guys predict one of these, just like we've done the other ones? Let's try it. What if I said arsenic 73 decayed by electron capture? What would it form? Perfect. 73 plus 0 gives me 73. 33 minus 1 gives me 32. And element number 32 on the periodic table is germanium. Excellent. You guys can do that on an exam? Again, one of the important parts is to remember and recognize that electron capture is absorbing an electron, right? Because other than that, it's a lot like beta emission. Just the point is, where do we put that electron? Any questions, or can we move on? Feel good about that? No questions or comments, and nobody wants to move on. Okay, we feel good about that. All right. Next, we have nuclear fission, or just fission for short. Fission occurs when a nucleus falls apart. It's just too big for its own good, and converting protons to neutrons and neutrons to protons is not going to help. It's just too big. And so it just splits up into more than one additional nucleus. Sometimes this occurs spontaneously, and sometimes we can encourage it to happen by bombarding a heavy nucleus with something like a neutron. So for instance, here's an example. Uranium-235 can decay by nuclear fission if we bombard it with a neutron. Basically, we take this thing that's prone to falling apart anyways, and we shoot it with a little bullet, and it goes, oh, I'm falling apart. Yep, sure am. And sometimes when we do this, we'll get the following products. So what we got here then was a krypton nucleus with a mass of 91, a barium atom with a mass of 142, and 3 individual neutrons that are formed as a result of this reaction. First thing I want us to confirm is that mass is conserved. So 235 plus 1 gives us a total mass of 236. On the right-hand side, 91 plus 142 plus, this is 3 times 1. Where's the 3 times 1? Should give us the same total mass, okay, because that's always conserved. 91 plus 142 plus 3, total mass of 236. Okay, if you ever see a coefficient here, don't neglect to apply it, okay? Total positive charges on the left-hand side are 92. Here we've got 36 plus 56 plus 0. Okay, let's just confirm. 36 plus 56 plus 0 gives us a total mass of 92. Oops, hang on a second. Awesome. Can everybody see how mass and charge was conserved there? Robin, do you mean what determines which atoms are formed, or what determines whether or not it will split? That's a really good question. And it probably depends on how it's struck, because in fact, if I strike uranium with a neutron, this will not be the only mix of products that I get. I might get other products as well. So it might depend on the angle that I hit it with. Like if I shoot it in the middle versus if I shoot it in the side, then it, it'll split off into more even pieces or maybe less even pieces. I don't know if that makes any sense. I will never make you predict all of the things that could be formed, but I could have you predict one of the things that could be formed, right? If I gave you all the other pieces. I'll show you what I mean, and that should make sense. So for instance, and this is in the lecture notes too, uranium-235, if I hit it with a neutron, it could also decompose to form a different set of products. It could decompose to form something plus tellurium-137 and 2 neutrons. Could you guys predict what this would have to be? Excellent. Candace and Joyce and Robin. Oh, hang on, Robin. Mass is off by just a little bit. because it should be, yep. So 235 plus 1 gives us 236, and then I'm going to subtract 137, and I'm going to subtract 2, and that gives me remaining mass of 97. Remaining mass of 97. And then 92 equals 52 plus 0 plus 40. So element number 40 must be zirconium. Right, so again, we had 235 plus 1, so mass of 236 on the left-hand side. If I subtract the mass that was taken up by the tellurium and the 2 nitrogen atoms, that gives me mass of 97. And then I had a total positive charge 92 plus 0 on the left-hand side. I subtract the 52 from the tellurium and the 2 times 0 from the neutrons which are formed, and I get 40 positive charges, so that must be zirconium. Do you guys feel good about being able to do something like this on the exam? Again, just fill in the blank. Okay. Now this is interesting because nuclear fission is used in our nuclear reactors, which give us electricity. And I want you guys to notice that in order to initiate this reaction, in order to help it go, I'm going to shoot it with a neutron, right? But both of these reactions produced more neutrons as products. I started with 1 and now I have 2. So these are also what we call chain reactions, because this products, these neutrons are also going to hit other nearby uranium nuclei and initiate additional fission. Okay, so for that purpose, nuclear fission has to be very carefully controlled, because if we weren't careful how we were doing it, these extra neutrons could just shoot off and interact with more uranium, which would create more neutrons, which would interact with more uranium, and then the whole thing could get out of hand very quickly if it's not carefully controlled. So that's why we've got kind of this danger of a nuclear meltdown. It's because the products then feed the initial reaction and it just gets hotter and hotter, and might exceed our capacity to hold and contain that reaction. So that's nuclear fission. Next, we have nuclear fusion. In nuclear fusion, I'm combining 2 smaller nucleuses to make a bigger one. It's the opposite of fission. So fission, it's falling apart. Fusion, I'm mashing them together. Okay, and this is what is done in the sun. You get hydrogen nuclei combining to form helium nuclei. And the reason that nuclear fusion is important, among other reasons, because fission is what we use in our nuclear power plants, but fusion is what is done in the sun. And this process releases a tremendous amount of energy. And so here's one case where we might choose to draw the energy as a product to say, hey, by the way, yeah, it makes a helium nucleus, but what's awesome about this is that it produces so much power, so much radiation, which we then might be able to harness as energy. So this is when, if you hear people talk about cold fusion, it's because this is a process which occurs in the sun, releases an enormous amount of energy. If we could replicate it here on the Earth, then it would give us an enormous amount of energy as well. But the problem is, this works really well in the sun because of the conditions of heat and gravity that are there that are really hard to replicate here on Earth. And so cold fusion doesn't mean that it's happening at cold temperatures, just like cold relative to the sun, basically. Colder than the sun. If we could manage to bring it down a bit, that might help. And so cold fusion It's kind of the holy grail of energy research, because there's lots of hydrogen on the planet. And if we could get a fusion reactor working, then it would be a lot safer than a fission reactor, theoretically, because then we don't have to worry about the chain reactions running away with us. And it could provide really clean energy, because we don't have then these other radioactive byproducts that are formed as well, because we just form helium. But the sun will do this. It'll form up to helium, and then once it runs out of hydrogen, it'll start fusing helium nuclei together, or helium with hydrogen. And our sun will go all the way up to carbon. Other suns will fuse all the way up to iron. Any elements heavier than iron are formed when those heavier suns go supernova, and they get fused in that process. So that's kind of fun. That's nuclear fusion as it occurs in nature. Again, I want you to notice mass on the left, 2 plus 2 gives me 4. Charges on the left, 1 plus 1 gives me 2. We can track this. Additionally, we could use fusion in the lab to make new elements, because we've got up to about, let's see, 111, right? But if we wanted to make bigger ones to figure out what they're like, then we're going to try to use fusion and mash this stuff together so that we can get bigger and heavier nuclei. So, for example, here's another one, silver, 109. If I shoot it with helium, I can get those two to fuse together to give me molybdenum 113. You guys notice mass, 109 plus 4 gives me 113. Charges, 47 plus 2 gives me 49. Okay. Everybody follow that one? You agree that that could happen? Sometimes when this occurs, we'll also get other byproducts, like it fuses but kind of imperfectly, and some other stuff is kicked out as a result. So for instance, I can make californium, which is 246. (98) by fusing uranium-238 with something else. But I also get a byproduct of 4 neutrons. Just get kicked out of the... Oh, I'm sorry, Candace, is 49 not molybdenum? Yes, you're right, 49 is indium. You're right. You get indium. Excellent. Good catch. Good catch. You're exactly right. All right. Help me out here, though. Can we fill the blank to figure out what I must have tried to fuse with this uranium atom to get it to form californium? So named because it was discovered, or the credit goes to the group at UC Berkeley in California. This is why people try to discover it, because if you discover it, you get to name it forever. Excellent, Joyce. So on the right-hand side, I've got 246 plus I have 4 neutrons. So I have a total mass of 250 on the right-hand side. If I subtract the 238 from the uranium, then whatever I did must have had a mass of 12. Good. And then from 98 positive charges plus 0 on the right-hand side, minus 92 gives me 6 positive charges on the left-hand side. So I've got a mass of 12 and 6 positive charges unaccounted for. And element number 6 is carbon. Well done. Can you guys do that on an exam type setting? Ten times. All right. One thing I do want you to notice before we continue, the way to tell the difference between fusion and fission The key is you're looking for whichever side has the highest molecular weight atom, right? So my options are 235, 91, 142. Okay, so this is the heaviest thing, so it must have fallen apart. 235 versus 97 and 137. This is the heaviest thing, so it must have fallen apart. For fusion, then, you're going to say 2, 2, 4. Okay, so this is the heaviest thing. So it must have been fused together. All right. This almost looks like alpha emission because I'm producing a helium nucleus, but the helium nucleus was not kicked out. It was formed from fusion because this is the heaviest part. Again, 109, 4, 113. This is the heaviest piece. Therefore, that one's fusion. 238, 12, 246. This is the heaviest piece. So that one's fusion. Okay. I do see some confusion with that sometimes. Okay. That is actually it. There is also gamma radiation, but gamma radiation, that's a terrible gamma. Gamma radiation, that's slightly better. It sometimes might accompany fusion like it did here, or fission or other forms of radiation, but it's not itself just ever kicked out from a nucleus, if that makes sense. Megan, heaviest thing in products for fusion versus the heaviest thing in reactants with fission. Well, unless I give you a theoretical element 112, 113, 114, that 111 is about it, right? This is what's been found so far. Actually, I think we might have done 112 as well. But I could give you a theoretical one up here just to see if you can do the math. Did that confuse you more? Let's look at the in-class activity sheet, because I think while doing some of this, it'll become a little bit clearer. Oops. Okay, so if we did, for instance, let's do this one, and this one, and this one. Here I've got bismuth 209 reacting with iron 58, and I formed something here, plus meitnerium 266. Can you guys tell from the masses and from the charges what this is going to be? Candace says it's a neutron. Robin agrees. Okay. We've got mass of 209 plus a mass of 58 on the left-hand side, minus a mass of 266 from meitnerium gives me a mass of 1 unaccounted for. Great. 83 plus 26 on the left-hand side, minus 109 on the right-hand side gives me 0 charges. And so based on the fact that it's got a mass of 1 and no charge, that means it must be a neutron. Excellent. Well done. And Candace correctly identified this one as fusion. Why fusion? There's on the right-hand side, right? Because the largest mass is a product. Yes. Yes, yes, yes. Okay, guys, help me out with this next one here, right here. Boron 10, strike it with a neutron. What do I get? I get helium 4 and excellent. 10 plus 1 is 11. So 4 plus 7 is 11. 5 plus 0 is 5. So 2 plus 3 is 5. And element number 3 is lithium. Is that fission, fusion? What is that? Fission. Excellent. Fission because heaviest things on the left. All right, help me out with this one. What am I going to get? So 59 plus 0 gives me 59. 28 minus 1 gives me 27. And then element number 27 is cobalt. How would you describe this one? Excellent. This one is electron capture. Where did everybody else go? Or is Candace the designated speaker for their class? Everybody's like, she's got this. I'm just going to watch. They'll be okay. Is anybody else with us? Okay. All right. Just making sure. All right. Any questions on this before we move on? No questions. Okay. Before we talk about half-lives, I do want to talk a little bit about gamma radiation versus alpha radiation versus beta radiation. So we have alpha, beta, and gamma. And we know that the alpha particle consists of a helium nucleus. And the beta particle is actually just an electron. And gamma radiation isn't a particle at all. It has a mass of 0 and a charge of 0. It's just pure energy. That's all it is. The reason that these properties are important is because that's going to impact how much energy they carry with them and how much damage they can do and how easy it is to stop them. Okay? So because all radiation can be dangerous in that these particles or this energy is sufficient to ionize surfaces that they come into contact with. So your atoms in your cells can become ionized and then they become more reactive and then that can cause damage. So damage is something that we don't always want. Sometimes we want it if we want to harness it to do something else, like kill cancer. But if we don't want to get cancer, we might want to avoid it. So which of these do you think is the easiest to stop based on their properties? Alpha and beta have charges. Alpha has the highest mass. Gamma has 0 mass. It's based on size that makes them more easily blocked. So the alpha particles, just because they're bigger, they're easier to block. So alpha radiation, if I have like a piece of paper or even the outer layer of your skin, is going to block alpha radiation. So that's pretty easy to block. It's not dangerous unless you have it internally, in which case your skin isn't going to help you, right? Beta radiation takes a little bit more. You need a couple layers of clothing or wood to block beta radiation. But gamma radiation, you need a really thick lead or concrete barrier. Because it just doesn't have any mass. It's just going to kind of shoot right through whatever you've got. Each of these can be gotten around if you take a radioactive dose of something. For instance, let's say you took a dose of something like carbon-11, which produces a positron emission, which creates gamma rays when it reacts when it's released, then that would produce gamma radiation on that spot, and that could be dangerous, or it could be helpful. For instance, positron, everybody heard of positron emission topography? Or a PET scan? So nuclear chemistry is actually used a lot in medicine these days, a lot more than people realize, because we can use it for imaging, and we can use it to treat tissues as well. But here's an example. A PET scan is an imaging tool that's going to give you a dose of sugar or glucose, which is carbon-based, that is radioactive. It emits electrons. Where do they get radioactive sugar from? Well, if you use radioactive carbon atoms in your sugar, then you'll have radioactive sugar. So you feed somebody radioactive sugar, you wait a certain period of time till the sugar localizes into the places that it's working, and then you image that area and you can see how the sugar has been uptaken and is being used based on the release of the gamma rays at that point position. Okay. Usually this is done as a brain scan because your brain feeds on sugar, glucose, almost exclusively. So if we want to look at your brain and try to image certain areas to see which areas are working harder and which areas are not working at all, then we might do a PET scan to do that. Minimally invasive, it's a lot easier than cutting into your brain to look inside to see what's going on, and can tell us interesting things. So nuclear chemistry, from the standpoint of medicinal chemistry, is a really big field right now that you guys should be familiar with. That's just one thing you guys should look up some more. Post about it in the discussion forums. That should be useful. Okay. I'm actually going to stop this recording and start a new one on half-lives.